Well, hello. Hello. Thank you very much for coming. I'm slightly surprised to see anyone here because this is essentially something you will never, ever want to do. So we are going to be talking about almost every detail you need to get .NET code running from scratch. And as I say, if you ever are thinking about how to solve a problem and you think, I know, I'll write my own .NET runtime, I would highly recommend you go away and think about it again. Microsoft do this very well. There is no reason for anyone else to do this. Now, of course, if you're thinking, oh, it might be fun to write my own .NET runtime, that's a completely different matter, and I would highly recommend giving it a go because it was quite fun in a very kind of niche, techie sort of way. And that's exactly the kind of people I hope you are, because this is very niche, very techie. I will be going into, as I say, just about every detail of how to do this. Whether we can do that in 1 hour is yet to be discovered, so excitement for all of us here. So I'm Chris Bacon. My day job is I work for Google in the cloud .NET team, along with John and some other people. This is nothing to do with that. At Google, we are not writing our own .NET runtime. Do you want to make that very clear? This is totally not Google work.
Right now, anyway.
Not yet, yes. Who knows? No. As far as I know, there are no plans to do so either. OK, so let's get going. So just to be clear on what we're going to do, I have Visual Studio open here. On the right, I hope you can see that. We have a couple of projects here. We have a classic Hello World. This is a C# project, which has, let's shrink that font size slightly, which has console.writeline, Hello World. And what we're going to try and do is write a program in C, not C#, C, that can take the DLL produced by the C# compiler and execute that code. Now, this actually is too difficult, it's too ambitious, too complicated. So what we're actually going to do is we're going to take this code and execute that. And you will see this is still fairly complicated, but this is, I hope, manageable. Right, so we're just going to build that. Now, I've already set up a build rule to copy the executable into the correct place. And the correct place is the same directory as this C file here. Now, I'm not an expert in C. I haven't done a lot of C for many, many years. So I apologize up front if my idioms are wrong, my casings are wrong, my whatever is wrong. Please don't tell me about it. Maybe at the end you can come and criticize my C. But it's not something I do anymore regularly. So I have here a C file. Now, the talk did say this was going to be from scratch, but you can see there is already code here. The code here is very minimal, and it's actually almost completely type defs, struct definitions rather than actual code. So we are basically going to write all the code from nothing at all. So just to quickly whiz through what's here, we've got some standard includes. We've got a few macros that I'll describe later. We have a function called crash, which just prints out an error message and exits. And then we have a whole load of structs and the type defs to the structs. Some more macros, and then, again, as you can see, struct after struct after struct. And we'll come to what these are in a moment. The reason I've predefined them, is because it's just a bit tedious copying them out of the specification. And if I get these wrong, it all goes horribly wrong very, very quickly. And then there's this quick array here, which, again, the numbers are important. If I get it wrong, it's all very embarrassing for everyone. So I've pre-done that. So this is our actual code that we're starting with. If you don't know C, hopefully this is very clear. I'll just run it. And ta-da! Press Enter to exit. There we go. It works. Good news. Right. So let's make a start. Now, the document you need to do all this is the ECMA standard 335. This is the full, tedious, and detailed specification of how .NET works. As you can see, it's the CLI partitions 1 to 6. And if we whiz down to the contents, you can see you've got content architecture, which is good to read just to get a general idea. You've then got all the details of metadata, semantics, SIL instruction set. So the SIL instruction set still stands for Common Intermediate Language. Is that right? Yes. And that is what the C# compiler actually produces. It produces still. So when we say, x equals 1, it produces, var x equals 1, it produces the IL to execute that. Okay, so this is a very detailed document. There's all kinds of stuff in the contents that we're not going to talk about. And that's not the point. I'm not going to explain some of what I'm going to do because there isn't enough time. So some of it I will explain as I go along. Other bits I hope just kind of pick up as we go along. Okay, so this is the doc. And this is a directory where main.c is. And as I say, I've set it up to copy helloworld.dll to that directory. And when we run this, I've arranged it in Visual Studio that it passes helloworld.dll as a parameter. So the first thing we need to do, right, here we go, C coding. There's going to be a lot of it. I hope you enjoy it. Right, we need to load that file. So we're going to load the file, and we're going to pass it argp1, which in C, the offset 1 is the first parameter. Offset 0 is the name of the executable that's actually running. So we need now to write a thing that loads a file. So we have a method called load file, which currently returns nothing, but it will return something later on. We're going to load the file, and just to say what we're doing, and just to prove, we'll just run that to prove that we're passing in. Right, so we're going to load file helloworld.dll. Right. So, load a file from disk. How do you do that? Told you we're going to start at scratch, doing everything. We first of all open the file. We say we want to read it. It's a binary file, and we want to have read access to it. That returns an int file descriptor. We then need to find the length of the file. This is a little bit tedious. We could memmap it, but memmap isn't portable, and I can never remember the Windows way of memory mapping things. So instead, we seek to the end to find the length. We then seek back to the beginning to go back to the beginning. We then allocated some data using malloc because it is C, so we have to actually allocate data for the right length. We then read the file contents. And then, because I'm a good citizen, we close the file. Okay, so that now has loaded the file into a memory in the program. Now, executable files in Windows have, ever since the MS-DOS days, contained a marker at the beginning of the file, which is MZ, which apparently were the initials of a very early MS-DOS programmer. I don't know who they were. So what we can do is we can just verify that this file does have those values. So we will say, now this is one of my macros, val. All it does is it takes a memory pointer, a pointer which in this case is pdata, offset 0, casts the result to a pointer to char, and then dereferences the pointer. So it means I can read a value at a particular offset from a memory pointer without having to worry about types and other inconvenient things. So this one should be M. And what we're going to do is we're going to crash if this isn't right. And this one should be Z. Oops, Z, capital Z. Okay, so that's good. And then if we, and now we know it isn't executable if it's got MZ. And we just run that, and it isn't executable. Excellent, we've passed the first hurdle. Good news. Right, so now, the question is, what do we do? We've got this big blob of memory that somehow contains that C# program, but how do we run it? So we turn to the manual, and this is the part we need, section 2, section 25, the structure of the runtime file format. So let's go here. Right, so we start off with an MS-DOS header, as I explained, which has the MZ, that's 4D and 5A, and then the thing we need is this LFA new pointer here. And this is a pointer that tells us where the next sort of header is in this file. So we're going to say LFA new equals, and again using our macro to read an int from, now I will actually just define a PMS-DOS header, which is the same as the data because it starts at offset 0 in the file, but it just makes it slightly clearer that which header we're currently reading into. So LFA new plus, no, not LFA new, sorry, LFA new equals that, and then the offset we need to read it from is 3C in this file, as the manual told us. So we read that, and now we have an LFA new. And as the manual says, I don't know if you can read that to make it slightly bigger. An unsigned integer offset LFA new to the PE header. The PE header is the portable execution header, so that's where we're going to go next. So we're going to make a pointer to the PE header, and I've got another macro which just allows me to get a pointer at a particular offset. Now we're going to do +4 because the first 4 bytes of the PE header are just PE null null, which are not interesting, so we're not going to view those. Very good. And now we want to we want to go and look at the definition of the PE header, which is here. And you can see here the first thing that looks interesting is that at offset 0, there should be a value that's always a fixed value, so we can check that. So now we can say if val, we've got the PE header, and it's a short because it's a 2 byte, I think that's right. Yep, so the size there is 2 bytes, so offset 0. So it's a short. So we read a short from P header at offset 0. And if that is not the value specified, which is 14C in hex, then we crash and say this is not a .NET executable. Terrible news. But if it is 14C, then we say it is a .NET executable. Big smiley. Right. Oops. Oh, there we go. Right, so again, we can now run that and see if it succeeds. It succeeded. It's an executable and it's a .NET executable. Good news. Now I've forgotten to put the character returns on the end. I get too used to write line in C#. Okay, so we just run that, and there we are. It's an executable, and it is a .NET executable. Good news. Okay. Right, we now have to go and look at what comes next. So, immediately after the PE signature is the PE file header, which we've just looked at. It then goes into a bit of detail about some of these flags that we're not interested in. I should say we're doing the absolute minimum necessary here to get to the actually executing code. We will do nothing unless we have to. And that means we're not verifying anything, we're not error checking, we're not doing anything like that you would normally do. Right, immediately followed after the PE header is the PE optional header. Right. And so immediately following, so we can go and look at this and see this is 20 bytes long, the PE header. So we can now say the PE optional header is a pointer that starts at the MS-DOS header, but at an offset of 20. And so that pointer macro just lets you get pointers, offsets to other pointers. Yes, you may be right, thank you. Great. So we now have the optional header. And then also, if we just whiz down a bit further, we can see there is a, where is it? There's another header we need called the PE section header, which actually I think we'll get to in just a moment. And back at the PE header, the only other bit we need from this PE header is this number of sections. And I'll explain what this is in just a moment and why we want it. So we will get a variable, an int, which contains the number of sections in this file. Now, a section is to do with how data is represented in these executable files. So they're split up into sections, and then the addressing is kind of on a section relative addressing, which we'll come to in a moment. So number of sections, it's a short, and it's at the PE header, and it's an offset 2. Great. So now we can print out how many sections we have. Okay. Excellent. Let's run that again. And we should have a sensible number of sections. We do. 3. It seems reasonable. Right. So now we need to load the sections. So we will loop through all the sections. I did warn you, every detail was going to be gone through. So this is one of those details. So each section contains a bit of memory that we've loaded in the file, and then it has like a virtual base address, and then all future addressing is via that virtual base address, not the actual kind of offset in the file. So we find a pointer to the section. Oh, no, before that, we need to get the section header, so which follows the optional header. So we have the section headers. The headers, because they're just sequentially in memory, they're not, there's no indexing into them, they're just sequential. So we need to find out how long the optional header is, and then it's just after the optional header. So the optional header, as you can see, is there's something at an offset 96 that has a size of 128. So what's 96 plus 128? That's 224. So the offset from the optional header of 224, that is the section header. Right, so to load the first section, we have a pointer from the section header. Oh, let's go and look at what the section header is, first of all. Now, down here, somewhere, we have the section header definition. Right, so here you can see each section header has a format following a total of 40 bytes per section header. And this is the content. So as I say, virtual addresses and the pointers to the raw data. So we have to kind of copy some data around so we can access it later. Right, P optional header. So we're going to do I times 40 because the optional, not optional header, sorry, section headers. P section headers. So we create a pointer to this section header, this section. Right, we then have to, I've got a struct already defined called RVA. Now, RVA stands for relative virtual address, and it just contains the base address, the size, and then the actual pointer to where we're going to store that memory. We'll malloc some memory in a moment. And then pnets, because we create a linked list of all the RVA sections, rather. So for each one, we create a struct. Now I've got a handy macro that generates allocs memory for a particular struct and returns a pointer to it. We then need to, by the way, you might be thinking, crumbs, have already been going for a quarter of an hour and all we've done is this. I must tell you that unfortunately, exciting that will be when we get to actually executing code, it's only a small part of what we have to do to get there. And this is all the getting there. So, right, we'll carry on getting there. So we need to set the base address, which, as you can hear, is this virtual address. And these are the addresses that the rest of the file uses to, so we set the base address to the virtual address, which is at offset 12 and it's size 4, so that's an integer. So we have an integer p section, and it was offset 12, wasn't it? Yep, offset 12. We set the size to, again, that's here, virtual size offset 8 is an integer, p section offset 8. Now we actually set the data. Now we now know the size of it, so now we're going to calloc this, which clears the memory to 0. And the reason we're doing that is because sometimes the size of the claimed size of the section is not actually the size of the raw data, and we want it 0 filled so that we don't end up with garbage in our data, and calloc pre-0 fills it. We're then going to get the RVA offset, which is this pointer to raw data here. So it's offset 20, it's an integer. So again, we use our handy macro to get at what's at offset 20. And now we do a memory copy to copy that data into the area we've just allocated. So the destination is the memory we've just allocated. The source is the offset. We've just read the RVA offset, and it's the offset into the entire file from the beginning of the file, which is why we've done it from pdata. And then we need to the size. Now, unfortunately, for reasons I don't understand, you have to take the minimum of the claimed RVA size and the size of the raw data. It can be either, one or other can be larger than those. So that's at offset 16. Okay, so we've done the memory copy, and now we just connect up our linked list. So we say, but where are we storing this stuff? Good question. What we actually need to do is keep a record of everything we know about this file. So I just happen to have a struct called tfile. So we'll have a pointer to that. Now tfile, as you can see, we have a pointer to all the RVAs, and this is the head of the linked list that we're about to generate. I'll talk about the other stuff soon. So we need to allocate, so we'll allocate one of these. And now we can use that to store our RVAs. So we're going to say RVA between next, and this is just how to connect a linked list. Because we've calced it, it's the initial p file of PRVAs is null, so that's correct. And then we just need to connect up the linked list. So what we're doing is we're sticking each section in the beginning of the linked list. So now we have loaded our sections. Good news. Right, let's run that and see if it crashes. Hopefully it shouldn't. And it doesn't. Number section 3, we've loaded our sections. Good. So, what next? We've now kind of got our memory in a way that we can now use it when later on we're told to go and read an RVA address. We now know our RVAs. We've got all the base addresses sorted out. So now we need to move on. So far we haven't really done anything to do with .NET at all, really. We've just been fiddling around with memory and headers. But we're about to move on to something where we are dealing with CLI things, because we get to this CLI header. So the next thing we do is load and look at this CLI header. So the first of all question is, how do we get the address of the CLI header? It's in the file somewhere. And the way we do that is this entry here. So offset 208 in the PE header, we have the CLI header. Now, you notice it's 8 bytes long, so what is this? And the answer is, it tells you up here, each data entry contains the RVA. Now, that's what we've just been playing with. That's why we need these RVAs, and the size. So both of those are 4-byte ints. So basically, the first offset 208, the first 4 bytes is the RVA address, and then the next 4 bytes is the size. We're going to ignore the size and just read the RVA address. So let's load the CLI header. So we'll have a pointer to the CLI header. And now we need to load the RVA address. Now, how do we do that? Well, we're going to write a method called find RVA find data. So we give it the file. This doesn't exist yet. We're going to write it in a moment. And what was it we wanted? We wanted an integer from the, which header was it? Is this data directory? Oh, yes. So that's actually part of this thing called the PE. It's actually the optional header. Yeah, it's on the section of this optional header, so it's part of this optional header. So optional header at offset 208. Yes. Okay, so now we need to go and write this RVA find data method. So we're going to be returning a pointer, and we need to take a T file. The reason we need a file is because that's where the RVAs are stored, and then we have the address. So what does this look like? Well, we need to whiz through this linked list. So we start at the head. It's a bit tedious having to code all this by hand, but that was the promise of this talk. Oh, come on, why aren't you doing that? And then while PRVA does not equal null, so we go to the linked list. I can't type. And if we can't find it, we will just return null. Possibly we should crash, I'm not quite sure. Oh, yes. Yes, thank you. As I said, I haven't done C for a while. And this is a very simple comparison. So if the address is anywhere within the header, we have to return the correct memory address that is kind of where that would be. So we just say if PRVA, no, we don't. We'll say if address is greater or equal to PRVA base address and address is less than the base address plus the size, then we've got the right one. So then we return, so we have to return the RVA P data, but then we have to return the correct offset, so it's however far the address was into that structure. Now, I'm just going to make sure I get this right. Right, so we return, then we use this pointer macro, which gives us the correct offset into here. So it's the address minus the base address of this section. Auto-completion is not working. Okay, so that's done. That's good news. So now we can load, we've got the CLI header from the RVA. Now, the next thing to do is look in this CLI header, and there are some interesting things in this CLI header that look very, kind of starting to look familiar, the kind of things that we'd expect. So, major runtime version, minor runtime version. Let's print those out. So, runtime version. And these are, they're both shorts, they're offset 4 and 6. So we need short into the CLI header, offset 4, wasn't it? Yeah, 4 is the major version and 6 is the minor version. So we'll just print out these two things. And let's run that. And oops, I've spelled header wrong. There we go. And see what that says. Ah, it says nothing at all. So that means it's almost certainly got a bug in our find RVA. Oh yes, I know what I did. Let's just go to that. I made the elementary mistake of forgetting to move on to the next item in our linked list. Right, so let's run that. And there we are, runtime version 2.5, which I must admit, I'm a bit vague on runtime versions, but it seems about right. What?
I'm confused. I'd expect 4.0.
Ah, that comes later. Yeah, the 4.0, we'll get there. Right, so that's the runtime version, and yes, that's the CLI version, which would be the 4.0. Don't ask me the semantics of that, I don't quite know. Right, so we've got the runtime version. Now, this thing here, oops, entry point token. Now, the entry point of a program is usually the kind of where you start running the program. So this looks important. What is a token? We'll come to that later. But for the moment, we'll just record that. Now, we happen to have something to store this in our T file data structure, and it's just an integer. So we will use our normal method of reading integers and store that into the T file structure. So it's in the CLI header, and its offset is 20, and it's an int, as I said. So we'll do that, and we'll just print it out because it's quite interesting. Entry point token. Now we're going to print it as hex because that proves its interest. Okay, and we'll just run that. So there we are, entry point token. 6, lots of zeros, 1. Now a token is something about how .NET metadata is stored within the file, and we'll need to come to this a bit more fairly soon. But basically, the most significant byte, which is the 6, tells you which table, and we'll come to tables soon, which table this refers to, and then the other 24 bits are which entry in this table is it. So it's entry 1 in table 6, and we'll learn much more about that very soon. Right, so we've got an entry point token, and now we need to move on to the actual, what's called the metadata. So we have here an RVA and size to physical metadata. Now the metadata is literally everything about your program is stored in what are called metadata tables. So every method, every type, every parameter, every field, everything else you can think of are stored in metadata tables. So what we're now going to do is load the metadata, get a pointer to the metadata header, and then we will have to read through some of this metadata just enough that we can get what we need to execute the wonderfully exciting program we're trying to execute. So the first thing we'll do is get a pointer to the metadata. So p metadata, and again, if you look, this is an RVA, so we'll use our RVA find data method. That's our file, and the address is, right, it's the offset 8 into the CLI header. So we CLI header, comma 8. Okay, so that's that loaded. Is that right? No, silly me. I've forgotten to actually use our macro. Right, that's better. Right, that should build. Oh, we're still debugging. Yes, we'll stop debugging. Oh no, what have I done? I think I've just done this wrong. Yeah, that should be an int. Okay, right, so that's now got a pointer to our metadata, and we'll go into exactly what the metadata is very soon. And now, because if we go down to this definition of metadata header, which is now, where is this? Is this? Right, here we are. This is in section 24. So this is the metadata header. And one thing that's worth showing here is this version. And this is the CLI version that this expects to run on. So we can printf CLI version, that's an S, that's a string, and this fortunately is UTF-8. We'll just assume it's ASCII, which it is in this case. So that means we can just print it directly. We need to cast it, oops. We need to make that a char star, and we use our pointer macro to just get an offset of 16, because that's where it is, offset 16 into our metadata header. And so now if we run that, right, version 4.0.30319. Now this is much more, you may have seen that kind of number when you're playing with .NET code. So we really are getting to stuff that's now much more familiar. It's taken a while, there's been quite a twisty path, but we're sort of getting there. That's good news. Okay, however, I have to tell you, the most fiddly and annoying bit is still to come, but it won't take too long to get through it. Now, the reason it's fiddly and annoying is because of reasons of making sure the file is as small as possible. There's now a whole load of headers that just follow sequentially after each other, but they're all variable length and there's no indexing into them. So unfortunately, we now do have to do some nasty pointer arithmetic and just keep track of where we are in headers and all that kind of stuff. So I'll get through that as quickly as possible. So hopefully in 10 minutes we should be through that. But it's quite interesting seeing the kind of stuff that these headers contain. And, well, let's just do it and then you'll see. So we've just printed out this CLI header. Right, so here we are, variable length stuff. The version is a variable length string, so now you'll notice the offsets are not just simple numbers, they're now things like 16 plus m, 16 plus x, 16 plus x plus 2, and all this kind of stuff. So we now have to kind of keep incrementing pointers to, or offsets to keep track of where we are in strings. So the first thing we can know is how long was that version string. And fortunately, it tells us at offset 12, we have an integer that contains the length of that version string. Here's the CLI header still. So we'll get the version length by reading an integer into our metadata header at offset 12. We'll now keep track of an offset. So this is an offset into all these headers, which we'll initialize at 16 plus the version length. And that's because you'll notice that the variable length thing is at 16. We're going to add the version length. Now, fortunately, the version length already is dealt with padding, so we don't have to worry about that. So now we are here. So offset now contains 16 plus x. We now need to know how many streams are there. Now, I don't know why they're called streams particularly, and very soon you'll learn what this means. So we need to know how many streams there are, and that's 16 plus x plus 2, but it's 16 plus x, so that's offset plus 2. So we're going to find the stream count. So that's, again, it's a short because, it's a 2-byte number, so it's a short. And we're at p metadata, and our offset is offset plus 2. So let's just print out our stream count, just to make sure that it looks sane. Okay, oops, it's not important, but I'm a perfectionist. Okay, and we'll run this. And there should be 5 streams, and there are. There are essentially always 5 streams. And we'll come on to, well, actually, I can quickly show you. And the streams are, right, stream header. Right, these are the streams. The strings heap, the US and blob heaps, the GUID heap, and the tilde stream, which is by far the most complicated and the most difficult to deal with, but we have to. we'll talk about what these streams are for in a moment. We're only going to have to worry about the tilde stream and the strings heap. Right, so for each stream, we're now going to increment the offset by 4 because I've lost track of where we were. Where were we? I think we were in here, weren't we? Yes. So that gives us access to the stream's headers, which is what we now need to do. So each stream has a header that we're now going to read to find out what stream it is and where the data is associated with that stream in the file. So we are literally going to for loop through each stream. Okay, so we need to find the stream offset. And in the header here, you can see the offset is offset 0, and it's an integer. So we read an integer from the metadata at whatever offset we've now got to. The next thing is the stream size. We actually don't care about that, not going to verify our streams maintaining their size, but we will just read it because it's quite nice to just print it out so we can just check that everything looks sane. So it's offset +4. We now need the stream name, which is here. So name of the stream is null terminated variable length array of ASCII characters, padded to for length boundary with nulls. So we get a stream name char pointer, which is in the metadata, which is just pointer offset +8 because that's at offset 8. Right, and now we actually want to get, so the stream offset we have here, this integer, this is an offset into from the metadata header of where the actual stream data is. So let's get a pointer to that. So stream, let's just call it pstream, and it's a pointer, so it's based on the metadata pointer, but it's at stream offset bytes past the beginning of the metadata header. Okay, we now need to increment our offset for the next cycle around the loop, and then we'll actually look at these values. Now the offset increment is a pain. It's the 8 bytes of these two things plus this variable length thing here. So it's 8 plus the padding. So it's 8 plus, and then we get the length of I know string's unsafe, I don't care. We'll get the length of the string. We add 4 for padding, and then we AND it by the negation of 3, and that does the padding correctly so that it pads it out to 4 bytes. So that's that. That's our loop will now loop through all the streams. And let's just print out what streams we've found. So we'll just print out the stream name, and we should find that these stream names here, #GUID, #US, #blob, all these things, now we've found those streams, hopefully, if we've got all our pointers right. We have, look at that. We found all the correct streams, as expected. Victory. It may feel like a small victory, but we are getting there. Whew. Good news. Right, so what are we going to do with these streams? Well, we have to treat them each differently, so we'll now do a nice struct comp, which again is unsafe, don't care. If stream name is, now unfortunately, have I got my keyboard map correct? I have, good. We're going to have to deal with this tilde stream. Now this is one that contains all what are called the metadata tables. Right, so the question is, what are metadata tables? Well, let's go to the documentation. Right, here. So this is the definition of all what are called metadata logical format tables. So there's a whole load of things in here, some of which you can kind of think, oh yeah, I can see why that would be needed in a .NET executable. So some obvious ones, method def. This is a method definition. So let's just go and look at the details of what this actually contains. It contains an RVA. Now, to what, you might ask? Well, if we just whiz down here, it tells us. So it says the RVA, here we are. No, if RVA equals 0, then either it's an abstract method. If RVA does not equal 0, let me just make this bigger. Then RVA shall point to the SIL code stream in this file. Yes! Finally, we've found some IL to execute. We haven't actually found it yet, but we now have we're reading the right documentation. So this is really good news. So back up to what else is here. There's some flags, there's some more flags, there's a name. And yes, that really is the name of the method. And then there's what's called a signature. Now, the signature is everything apart from the name that defines this method. So it's like what the return type is, what the parameter types are, any generic constraints, all that kind of stuff. We're not going to care about signatures at all in what we're doing today. And then it contains an entry into the parameters so that you can find out about the parameters, like the names of the parameters, the types, all that kind of stuff, and the order of the parameters. Let's stop running. Right, so how do you load these tables? We do it by going and looking at the documentation yet again. Where were we? Right, that's about a particular stream. Right, here's the tilde stream, yes. So this is the, so the data we've got for the tilde stream points to this structure. And we don't care about any of this apart from, the first thing we care about is valid. So there can be up to 64 tables. Valid is an 8-byte, 64-bit number, and it's just a bit field saying which tables are valid in this particular file. So there can be up to 64 tables. In this file, there will be nowhere near 64. So we need to go through this bit field, finding out which tables are valid, and then the first thing we have to do is find out the length of all these tables. And as you can see, this entry down here, tables, this is the sequence of physical tables. What it actually contains is, first of all, it contains a list of all the lengths of valid tables, then it contains the actual data in the tables. So the first thing we have to do is find out all the lengths of the tables, which we will do. So long valid. So we first of all read that valid header, which is a long, which is in C. That's how you do a 64-bit number. There's probably other ways, but this is one way. And that's at offset 8. There it is. We then have to get a pointer to a row counter pointer. So as I said, the first thing it contains is the length of all the tables, which is at offset 24. So we go find a pointer to offset 24, and we have an int. They're all ints, the length of the tables, so we use ints. And now we have a for loop through, so we'll have a couple of variables here. We'll start j at 1, which is the bit. I is counting how many bits, and j is the bit mask. So we cycle through here, and we say if valid and j, so that means if this is a valid table, then we record something about it. So in the pay file, we also had an entry for these tables, which is a 64 entry array of counts and pointers. So we, in this sort of loop through, we set the count, and the count is wherever the integer that the row counter pointer is pointing to. And then we have to increment the row counter, but only for valid tables. Now you might say, if you don't know C, doing a plus equals 1 doesn't increment by 1 byte, it increments it by 1 of whatever it's pointing to. And so we're pointing to int, so that's going to increment it by 4 bytes. So that's now got the lengths, that's good news, and now we actually load the data. So we have table data equals p row counter, because the table data starts where the row counter, the row entry is finished. We'll print something out, we'll print that we've, now we're just going to print out, as we load each table, we're just going to print out something about it. So we'll just print out that to start with. It's less than 64. Again, it can be up to 64 tables, so we cycle through 64 times. We look in our previously stored area to find out how many rows there are in each table. And if count does not equal 0, then we need to load this table. So first of all, we look at the table size, which is, right, this is how many bytes each entry in the table takes. Now this is, I've had a bit of a shortcut here, because if you go and look at some of these definitions of method def, for example, this is what's in the table. So we have a 4-byte constant, a 2-byte flag, another 2-byte flag, and then a name. It doesn't tell you how many bytes it is. Why would they do that? And the answer is because it's variable. But it's variable in a very constrained way. So it's either 16 or 32 bits, depending on how many entries there are in this table. So if there are more than 2 to the 16 entries, it'll be a 32-bit. If there's fewer, it'll be 16-bit. We're only dealing with small files, so they're always going to be 16 bits in this case. So I've hard-coded it to 16 bits. You can't do that in a real system. But that means that I know at compile time the size of all my tables, so I've just stuck those in an array, and that was one of the arrays I showed you at the beginning, and I said it's important these are right. So that's the table size. Right, we're then going to allocate some. We're then going to allocate some memory to store the. Let me just. Right, we need a pointer for each entry in the table, and we're going to do +1 because the table tokens have 1-based indexing, not 0-based. So it's quite handy just to not have to worry about that. And we'll set the first entry, the 0th entry to null. Right, we now need to go through each item in the table and copy it to the right place. Now you might ask why we're doing this at all. Why don't we just not copy it anywhere? And the answer is that we need to store a little bit of extra information along with each item in the table. So unfortunately, we need to have somewhere to store that extra information. There are various ways of doing it. I chose to do it this way. Now, the prefix is the extra information we want to store. So we need to allocate something that's got the size of the prefix plus the table size, which is the size of each entry in the table. And then we're just going to set the only thing we actually want to know is the file that this table entry came from. So we store that in the prefix, and then we have to memory copy. Now again, prefix plus 1, that just skips past however large the prefix is. And then our table data is our incrementing pointer of where we are through all this metadata. And we copy the table size. So that's good, that's done. We then, we then set our, so we've got an array that contains all the pointers to its data, so we now set that to the prefix. It's not just a prefix, it contains the prefix plus all the data. It's just, and then we need to increment our table data pointer. It's a void pointer, so we can't just add to it. And what we actually need to do is add on the size of this particular table. So that's done. So we've now loaded all our data, and we will triumphantly print out the fact that we have loaded table ID whatever, and we will show how many entries we have in each table. So it's table ID, and it's I from the outer loop here that we're iterating over, and it's count, which was how many entries we have. Now, if this is all correct, and this is where it could all go horribly wrong because there's a lot of pointery stuff. No, but there we are. So we've loaded those tables, and that tells you how many entries there are. So just quickly, table 6 is the method def table, and you can see we've got 2 entries in our method def. That means within the Hello World program that we compiled using the C# compiler, we have 2 methods. You might say, 2 methods? How can that be? There's only 1 method in your program. But of course, this is a non-static class, so the compiler has auto-generated a constructor for us. That's the other method. So when it says method def, it literally means, it doesn't just mean what we think of as methods, it also means constructors and static constructors or class constructors.
So to make that static and rerun.
Well, yes, we're running out of time, so I'm not going to do that. And we still haven't executed any code. Right, so, but this is really good news. So we're done. We can now return our file. So we need to go and change the signature of this method to return a tfile pointer. And we need to store the file. Whew. We have loaded a file. Yes. We now have 12 minutes left to execute something in this file. But the good news is that was the hardest bit of this by a long way. So now we really can get on to more interesting things. Although that was quite interesting, I thought. It's not uninteresting. Now, I'm just going to organize all my paperwork here. I did take the low-tech solution of printing out the actual code, so I wouldn't have to remember every single bit as I was going along. Right. You remember we loaded an entry point token. That tells us what method we need to run first. So we need to load the entry point method. So we will do that. Now, you remember I was showing you the method def stuff. So this is a type I pre-wrote to represent that method def stuff. So we will have entry point method def, and we will call a method that doesn't yet exist, called get method by token, and we'll pass it the file that contains. Oh, fine, no, don't do that. Sorry, we'll pass it the entry point. Oh, no, we don't need to do that. Sorry, yeah. So we need to pass it the file and the token. Right. So let's write this method. We're going to be returning one of them. Oh, whoops. pointer to it. So we have a T file, and we have a method token. So how's this going to work? Well, we just need to load the right table entry for this token. Now, a method token, we've looked at method def, but there's also another way of referencing methods called method ref, which is where you want to reference a method that is not in your DLL. And obviously you can't do that with the method def because you don't have IL for it. So there's another table called method ref that we're not going to use, but the token could be a method ref token, not a method def token. So what we're going to do is we're going to extract the table ID from the method token, and then if it is a table ID method def, which is 6, then we can just return. Now, this macro is all it does. It just goes to the correct table in the file and gets the already loaded method def in this case from there. And then, of course, if that's wrong, we'll just crash because we can't deal with it. We'll say return null because the compiler complains if you don't return from a method. Okay, so now we've loaded that method. Check it builds. If I made a mistake, I've made a mistake. What have I done wrong?
The variable. You've declared that you'll...
Oh, yeah, thank you, yes, great. Okay, just build it. Good, no errors. So that's great. So what we can now print the name of this method, which is quite nice. Entry point method name. Right, so we have our p-entry method def, and look, we have a name. Name index, what does that mean? It means, remember the streams we were talking about earlier when we loaded the file? It means it's an index into the hash strings stream. So to read that, we will use another macro called getString, where we pass it the file, we pass it the offset, and that will give us the correct pointer, char pointer back, which points to the strings. Now, conveniently, these are UTF-8 strings that are null terminated in the file, so we can just reference them directly. UTF-8 will pretend they're ASCII. Now, it won't work because we didn't actually deal with the string stream here, so we'll just do that now. So if the stream name equals, what was it, hash strings, and equals naught means equal, then all we'll do is in the p file has a p strings pointer, so we'll just do that. So now we've recorded where the string stream starts in the kind of raw file data. So now if we run this, it should print out the name of our entry method, and it does, main. How about that? And look, it really was called main. You take all this for granted. Okay, good. Right, so what next? We are so close to executing code. So we have the entry point method loaded. We've got a reference to the method def for it. So what do we need to do now? What we need to do now is when you execute code, you have to execute that in some kind of state that keeps track of things like where you are in the code. In fact, that's all we need track of at the moment. So we're going to call a method called createMethodState. And this is going to create method state for this entry point method that we've just loaded. So we need to define this method. It will obviously return something in a moment. We'll worry about that in a moment. tmdf method def, p method def. Right, so what does it mean to create the method state? So the method state, right, we need to have a type, a struct, which is our method state. And what are we going to need? We're going to need a pointer to the IL. We're going to need an instruction pointer. That's an offset into the IL of where we are. And possibly that's all we need. Is that all we need? Locals, John says. We haven't got any locals. Who cares about locals? We'll also keep a reference to the file, which I think we might need later. I'm not quite sure. There isn't much later to go, but and we'll just type def that. Okay, so this is actually going to return a T method state pointer. So first of all, we'll create our method state method state T method state equals T, my handy macro to create one of them. Okay, so how do we load this stuff? That's a good question, and let me just double check how to do that. It would be embarrassing to get it wrong. Okay, so we have to go through a thing called the IL header. Now, fortunately, if you're thinking, oh no, not another header, it's a very simple header. So in the file, we look up the RVA address of the RVA, which, as we discovered earlier, is the address of the IL header. Now, the IL header, oh no, it's not there. Here we are. Right, this is the IL header. There are two types of IL header, a tiny one or a fat one. Slightly unfortunate naming. We're only going to have to deal with a tiny header, which is just 1 byte long. And in fact, I'm not even going to check that it is the tiny header. I promise you it is. So method state PIL is simply 1 byte after the IL header. Oh, sorry. Pointer, comma 1. Excellent. And in fact, that's all we need to do. We collect it, so the instruction pointer is already 0, so we can just return that method state. So that's good. So we have a method state. We need to store that. T method state equals create a method state, and now we can execute it. Woohoo! So we execute T method state. Okay, how do you execute IL? Well, and this is an interpreted runtime, so all we do, we just read opcodes, execute them one at a time. So we have an infinite loop to go through the opcodes. We load an opcode. Right, so this is an unsigned char. We're loading it for, now I'm just going to create a quick pointer straight to the IL. That's immutable, so we can just get a copy of that easily enough, and it won't change. And then the offset is the instruction pointer, the current instruction pointer. So let's just print out what we've... now we're going to print this out as a 2-digit hex. And here we have the opcode. And then what we're going to do is have a big switch, well, a small switch statement on the opcode. Which, of course, by default, it will just crash and say, cannot yet execute opcode. Okay, site duplication there, but never mind. Okay, so let's run this.
You're not passing in file at the moment.
No, we're not, thank you. My linter down there. Oh, sorry, no, p file is just a t file, p file. Where do I need file?
You haven't actually copied it into the method state, but you need it in order to... Yeah, in the...
Oh, I see what you mean. Yes, thank you. Thank you. That should be p method def p file. Great. Oh no, it's prefix p file. Oh, come on. Prefix.p file. There we are. Okay, does that build? It builds. Does it run? It runs. Oh, except it doesn't print. Oh, what have I done? %02x. Right, try it again. Come on. Oh, I'm still running. Right, run. And how about that? We can't execute opcode 2a. What is opcode 2a? You'll be glad to know we're like within 1 minute of finishing. So opcode 2a is, if we go to IL_spy, where I've conveniently already loaded this main method, so we're going to look at the, oops, not that, we're going to look at the IL, the C#, and you'll notice there's just one instruction, return, which is OX2A. So, and that's defined here. And they're not there, it's defined in the documentation here. as you can see, ret has opcode 2a, so we will make it so we can execute 2a. And what do you do with a return? You return. So, ladies and gentlemen, I present to you a fully running IL interpreter from scratch. Thank you. That was quite intense. But I hope it demonstrates to you that this stuff, which we completely take for granted, we don't normally know or care how it works. But actually, it's not that complicated. You can code that up in an hour, as I've just demonstrated. And although the only instruction we can currently execute is return, it's a shame we didn't have another 10 minutes, because if we had, it's surprisingly easy now to get a subset of CIL executing, like all the arithmetic stuff on integers. It's just trivial, completely trivial. The next thing I was actually going to, if we'd have had like 2 more minutes, I would have shown just returning an exit code from a program, which would have meant we'd have loaded a constant integer and returned it and then got it out at the end, and we could have displayed our exit code. So it's not that complicated. However, having said all that, of course, we've ignored so much. Like, we don't have a type system at all, let alone one that can handle generics. We don't have a heap at all. You can't load other assemblies at all. So all this stuff is actually, it does build up the complexity. But it is completely possible for one person to write a pretty complete IL interpreted runtime in a few months. And I know that because I did it a few years ago. It's never been used. Oh, well, no, it was used as a prototype. I don't know if you come across Blazor, which is this new C# in the browser thing. So their prototype used my runtime in their prototype. They don't use it anymore, but it was quite satisfying that they did initially. So thank you very much for coming. If you want to talk about anything, including questioning my sanity, then do come and talk to me at the end. Thank you very much for coming.